Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 5 on modeling with systems of equations. Now, most of this unit has been building towards this particular lesson, right? What we want to be able to do in this lesson is take real-world situations that can be modeled using a system of two equations with two variables and then solve that system by either using substitution or by using elimination. So let's get right into it and start to do some modeling. Now, you will want a calculator today just to do some routine calculations. So I've got my handy dandy TI scientific calculator that I'll bring out in a little bit to do calculations. I'm not going to be using my graphing calculator today because I don't particularly need that. Now, many real-world situations can be modeled with systems of equations. When we have two quantities related in two different ways, this tends to give rise to these types of systems. So let's look at a particular problem that involves money. Let's take a look. Darius has 9 bills in his wallet that are either $5 bills or $10 bills. Simple enough, right? Letter A. Fill out the following table to see the dependence of the two variables and how they then determine how much money Darius has. All right. So let's talk about this, right? We know just one piece of information right now, right? Well, two pieces really. Darius has 9 bills and they're 5s or 10s, okay? So, right, we can I want to just play around with this problem at first, then we'll start to model it with systems of equations. Like, if Darius has 0 5s, right, then the number of 10s he has to be equal to 9, correct? Because he's got 9 bills. Now, how much money would Darius have at this time? Well, he would have $5 times 0 5s plus $10 times 9, and that would be $90, right? So if all of the bills in Darius's wallet are 10s, then he must have $90. Let's do one more of these rows together and then have you do the other two by yourself. Now, if Darius has one $5 bill, then because he's got 8 bills in his pocket, he would have to have 8 10s, and the amount of money that he would have would be $5 times 1 5, $10 times 8 10s, and that would be $85. Kind of makes sense that it would be 85 because I'm kind of swapping one of those 10s for a 5, and I'm losing $5 from that total from the first line. Why don't you go ahead and play around with the last two rows here and figure out what each one of them would be equal. Pause the video now. All right, so if Darius had 2 5s, he would have 7 10s, and the amount of money he would have would be 5 times 2 plus 10 times 7, and that would be 10 plus 70, which would be 80. Likewise, if he had 3 5s, he would have 6 10s, and the amount of money he would be 5 times 3 plus 10 times 6, that would be 60 plus 15, and he would have $75, right? And all I'm doing with this particular table is just trying to get a sense for how the number of 5s and the number of 10s relate to each other, and how those two then get into how much money that Darius has. Let's take a look at letter B. If F represents the number of $5 bills and T represents the number of $10 bills, then what does the following expression calculate? Explain. The expression being 5F plus 10T. So think about that for a moment. What does this expression calculate if F is the number of $5 bills he has and T is the number of $10 bills he has? Pause the video now and write down what that expression represents. All right, well, that expression represents the amount of money that Darius has, right? The amount of money Darius has, right? And of course, the explanation is real simple. If I take the number of 5s he has and multiply by $5, that's how much money he has in 5s. If I take the number of $10 bills and I multiply by 10, that represents how many dollars he has in $10 bills. And maybe I should have actually said it represents the number of dollars that Darius has, right? right? Because it's really that. All right. Now, the second part of letter B says, give an example by choosing a value for f and a value for t. So for instance, we could even just go back to this table. If the number of 5s he had was 2, and the number of 10s he had was 7, right? Then I'd have 5 times 2 plus 10 times 7, and I'd have $80. Right? And it's very important to understand here that f doesn't represent the amount of money he has in 5s. It represents, oh, he's got 3 $5 bills or 7 $5 bills or whatever. And t doesn't represent the amount of money he has in 10s. It just represents how many $10 bills Darius has. All right, now let's get into the important part. Letter C. If Darius has a total of $55, set up a system of equations involving f and t that models the information given in this problem. Solve the system. Recall that he has 9 total bills. Okay, so let's set this up. Now remember, okay, I'm going to write this down right here. I'm going to write down some let statements, even though I sort of did it before. Let f equal the number of $5 bills, and I'm going to let t equal the number of $10 bills. Again, we already really defined that up in letter B, but I just want to be very clear about it. Because now, one of the two equations in our system is very, very easy, right? He's got 9 total bills, in which case the number of $5 bills plus the number of $10 bills is equal to 9, right? He's got 9 total bills, so f plus t must be 9. The other piece of information we know, though, is that Darius has a total of $55. So that means if I take that expression from above, 5f plus 10t, right, that's the amount of money that Darius has, that must be equal to 55. And I'm going to circle this right here because this is my system, right? That is the system of equations that describes all the information given in this problem. This describes the situation that we have 9 bills, and this describes the situation that I've got $55. Now I want to solve it. Now, I've got 2 choices. I could either solve this using the method of substitution or solve this using the method of elimination. Because both equations have both variables on the same side of the equation, it makes more sense to me to solve it using elimination. Now we did that in the last lesson, right? And we're going to have to modify just one of the 2 equations, I would suggest the first one, in order to eliminate one of the 2 variables. So I'd ask you now to pause the video and solve this system by elimination. All right, well, do I want to get rid of the f? Do I want to get rid of the t? Which one do I want to eliminate? I think I'll eliminate the f by multiplying the first equation by -5 on both sides. All right, so I'm going to take this, I'm going to multiply by -5 here, I'm going to multiply by -5 there, and that first equation then is going to become -5f minus 5t is equal to -45. The second equation I don't need to change. That's just going to be 5f plus 10t is equal to 55. Now when I add those 2 together, the f's eliminate because those are additive opposites. -5t plus 10t is just positive 5t. -45 plus 55 is 10. Divide both sides by 5. And it looks like the number of $10 bills that Darius has is 2. Okay, now we haven't completely finished off this problem because we also want to know the number of $5 bills that Darius has. That's very easy. You could probably almost just do it in your head, right? Darius has 9 total bills, and 2 of them are 10s. So 7 of them are 5s. But, right, the way that we typically do this with a system is we take that 2, we plug it into one of these 2 equations. I'm thinking the first one's going to be the easier one, right? And we solve. In other words, f plus 2 is equal to 9. Take me back to 6th grade algebra, f is equal to 7. All right. So Darius ultimately had 7 $5 bills and 2 $10 bills. And that is, of course, easy to check because I could say 7 times 5 is 35, 2 times 10 is 20, right? So I then have 35 plus 20, and that would be $55, which is the amount of money that Darius has. All right, let's change it up a little bit. Let's take a look at letter D. Let's say that we were told that Darius had 7 bills that were all 5s and 20s, and we were also told that he had a total of $120. Set up and solve a system to help evaluate whether we could have been told true information. Make sure to define your two variables with let statements. Now this is interesting, right? Reading this question carefully, it doesn't say, try to figure out how many $5 bills and how many $20 bills Darius has. It literally says, set up and evaluate a system to see if we could have been told true information. So there could be something that we run into that makes us go, well, that can't be true. All right. So what I'd like you to do is pause the video now, right? You're going to have to create 2 new variables. You're going to want to model the system of equations using the information given, very, very similar to what we just did. Solve the system and see if there's anything in there that makes us, believe that this couldn't happen, or maybe something in there that makes us believe that yes, this could have happened. Pause the video now. All right, well, I think I'm going to stay away from the variables that we used in the last one. Although you could certainly use F for 5s and T for 20s again, but just to kind of distinguish it between the two problems, this time what I'm going to do is I'm going to let X be equal to the number of $5 bills, and I'm going to let Y be equal to the number of $20 bills. All right, so just, I love using X and Y. They're simple. I know that they aren't the first letter in those words, but good enough, right? So what do we know? We're told that Darius has 7 bills. All right, so that's simple enough. That means if I take the number of 5s I have and the number of 20s I have, there must be 7 of them when I add them together. Now the other piece I know is that if I take the amount of money I have in 5s, which would be 5x, and add to it the amount of money I have in 20s, which would be 20y, that would have to be a total of 120. All right, so very, very similar to our last problem. This system now models all of the information we were told, and we can now solve it by either eliminating x or y. And I think, again, what I'm going to do is I'm just going to eliminate the x by multiplying both sides of the first equation by -5. All right, so I'll do a -5 there times -5 here. Let me make that dot a little bit bigger. That's going to make that first equation -5x minus 5y is equal to -35. The second equation is going to be 5x plus 20y is equal to 120. All right, I'm going to add those together. The -5x and positive 5x are going to cancel. The -5y and the 20y are going to give me positive 15y. And I think I'm going to bring out my TI Smart View calculator right now, just because, it's early and I'm not feeling like making any mistakes. So I'm going to do -35 plus 120 gives me 85. It's all good. I'm going to divide both sides by 15. No big deal there. So I'll get 85 divided by 15. Enter. And I get the number of $20 bills I have is 5.6 repeated. Now normally at this stage, right, I would take that, I would substitute it back into the first equation or the second equation to figure out how many $5 bills I have, but at this point we're going to stop and we're going to make a conclusion, right? We're always going to be thinking about our results in math. Math is about using mathematical tools to make sense of the world. And the plain fact is, right now, we are being told, in order to solve this system of equations, we'd have to have 5.6 repeated number of 20s. But the number of 20s has to be a whole number, right? It can't be a fractional number. It can't be a negative number. The number of 20s has to be a whole number. You can't have 5.6 $20 bills in your wallet. At least the 0.6 $20 bill would not count. You can't rip a 20 and be like, look, I have a portion of a 20. That doesn't work. All right, so the answer really, remember the question was, could we have been told true information? And the answer was no. No, this could not be true because we cannot have 5.6 $20 bills. It's not possible, right? You can have one $20 bill, two $20 bills, three $20 bills. You can't have 5.6 repeated $20 bills. I don't even know what that would mean, to be quite frank. All right, let's continue to model. More modeling, more modeling. Many situations can be modeled using systems. One of the most common that arises are problems that involve what are known as unit costs or costs per item, right? You know, costs per pound, costs per donut, costs per soda, whatever. So let's take a look at a great example of that. Exercise number 2. Louisa went to a concession stand and bought 3 pretzels and 4 sodas and paid a total of $11.25 for them. Raza went to the same stand and bought 5 pretzels and 2 sodas and paid a total of $8.25. Letter A. Could pretzels have cost $1.75 each and sodas cost $1.50 each? How can you evaluate based on the information given? All right, great. So this is very important, right? We were given 2 real pieces of information in this problem. One was about what Louisa bought and what she paid, and then the other one was what Raza bought and what he paid. Specifically, right, Louisa bought 3 pretzels, 4 sodas, and paid a total of $11.25. Raza bought 5 pretzels and 2 sodas and paid a total of $8.25. So what I'd like you to do is play around, certainly use a calculator, play around with this and see if these could have been the unit prices for this problem based on the information given. Pause the video now and see what you find. All right, well, I think it's obvious. What we want to do is, if these are the unit prices, we want to see how much Louisa would have paid for 3 pretzels and 4 sodas, then how much Raza would have paid for 5 pretzels and 2 sodas, and see if they match what we're told in the problem. It's really that simple. So I'm going to kind of lay it out first as Louisa, right? What Louisa would have paid would be 3 times 175 plus 4 times 150. So let's just, bring our calculator out very slowly and see if that would have worked. 3 times 175 plus 4 times 150. I'm going to do this all in one calculation on the calculator. And that's $11.25. Awesome. So far so good. Right, that works. And let's see about Raza, right? So for Raza, we were told he bought 5 pretzels. Let's see if it could have been the case, 175, and 2 sodas at 150. Okay, so let me just clear that out. Let's see if that also works out. 5 times 175 plus 2 times 150 equals 1175. Oh, no, right? That doesn't equal the 825. So although those could have in theory been the prices that Louisa paid, for Raza, right, he only spent $8.25, so those can't be the unit prices. Can't be. Let's take a look at letter B. Letting x equal the unit cost of a pretzel and y equaling the unit cost of a soda, write a system of equations that models the information given. All right. Well, let's do this together since you haven't done it before. Now, let's think about just Louisa, right? For Louisa, how much would she have spent on pretzels? Well, if x is the unit cost of a pretzel and she bought 3 pretzels, then she would have spent 3 times x on pretzels, right? And if y is the unit cost of a soda, 1 soda, and she bought 4 sodas, then she would have paid 4 times y for her sodas. And all of that would equal $11.25, right? It's just simply the way unit costs work. All right, get that there. Now, we can do exactly the same thing for Raza. In other words, right, we can say, well, Raza bought 5 pretzels and 2 sodas and paid a total of $8.25. So that would be 5 times the cost of 1 soda 5 times the cost of 1 pretzel, my apologies, plus 2 times the cost of 1 soda, and that would be equal to $8.25. And that is our system of equations. Okay, and yet again, just like the previous problem, we've got a situation with 2 equations with 2 variables, and all those variables are on the left side of the equation. That leads us to letter C. Solve the system of equations using the elimination method. Okay, so now we want to solve this system using the elimination method. Keep in mind, we're probably going to have to modify one or both of the equations in order to eliminate one of the variables. I'd like you to pause the video now and go ahead and do this. Now keep in mind, we've got some decimals involved here, so it's going to get a little bit more messy. Make sure to have that calculator handy. Use it, use it, use it. There's nothing wrong with that, okay? And you can either choose to modify both equations, or there is a way to just modify one of the 2 equations. Pause the video now and solve this equation to figure out how much 1 soda costs and 1 pretzel cost. All right, well, it's all about whether or not you want to do more work or less work. One thing I noticed right away is I've got a 4y here and a 2y here. I could easily make this 2y into a negative 4y by multiplying both sides of the second equation by negative 2. So that's in fact how I'm going to start this problem. So the first thing I'm going to do is multiply both sides of that second equation by negative 2. Okay, and that is going to give me the following equation. Negative 10x minus 4y is equal to negative 1650. That one I think I can do in my head, I think. All right, now what I want to do is I want to grab that first equation, which is 3x plus 4y equals $11.25. Write that down right underneath it, and let's do some addition. Negative 10x plus positive 3x is negative 7x. Negative 4y and positive 4y cancel. On this one, if you need to, use the calculator. Negative 1650 plus 1125 if you need to. That's going to be negative 525. Divide both sides by negative 7. We can just hit divided by negative 7 on our calculator here. And that's going to be x equals 0.75. Now I still have to figure out the value of y, and we'll do that in just a moment, but I'd like to step back again and always reflect on the answer I got and whether or not it makes sense, right? What was x? What was x? First, let me bring this out of the way. X is the unit cost of a pretzel, and it's $0.75. It's 75 cents. That's reasonable. And it's reasonable for a variety of reasons, some common sense, some a little bit less common sense. One of the reasons it's reasonable is it's not a negative number, right? There's no way we're going to get a negative cost. Another reason that it's reasonable is that it's accurate to the nearest hundredth, meaning that if I had gotten like 0.6375, that wouldn't have made a lot of sense. We don't pay 0.6375 for a pretzel, right? 75 cents for a pretzel, that's reasonable. I also didn't get $211.53. That would have been a very expensive pretzel. You'd only have to pay that if you were like at a Knicks game or something like that, right? So the plain fact is, this is a reasonable answer by almost any metric. Now, of course, I still need to figure out how much a soda costs. So I need to take my value of x and I need to plug it back into either one of these 2 equations and figure out the value of y. Which one should I put it into? It really doesn't matter. I think I'll just throw it into the first one. That's 3x plus 4y equals 1125. Give myself a little bit of room, so I'll do 3 times 0.75 plus 4y is equal to 1125. 3 times 0.75. Let me clear this out. 3 times 0.75. Yes, I'm doing that right now, is 225. 225 plus 4y is equal to 1125. Oh, I need more room and more room. Minus 225 minus 225. That gives me 4y is equal to 9. Yep. Divided by 4, and y is equal to 225. In other words, one pretzel costs 75 cents and one soda costs $2.25. Now you might think that's unreasonable. You might think, well, a pretzel should cost more than a soda. But again, it's a reasonable answer for all the same reasons we talked about before, right? It's not negative. It doesn't have decimals extending past the 100th level, all of those things. And that's important because if you got an unrealistic answer, it would tell you that either the problem had a design flaw in it, which can happen. We're all human. We all make mistakes designing math problems. Or, right, simply you've made a mistake somewhere. All right, let's do the last part of this problem. Here we go, letter D. If Parker went to the same concession stand and bought 2 sodas, how many pretzels would they need to buy so that they spent the same amount on both? All right. Well, at this point, we know the cost of a pretzel, 75 cents. We know the cost of a soda, $2.25. Use those and see if you can solve for letter D. All right, right? So Parker bought 2 sodas. Let's just 2 sodas. How much would that cost? Well, 2 times 225 from before. So Parker spent $4.50 on sodas, right? And that's all I know so far, right? We want to know how many pretzels Parker would have had to have bought in order for them to have spent the same amount on the sodas, sorry, on the pretzels as they did the sodas. Well, what we know is that we know each pretzel costs 75 cents. There it is. So if I do 0.75, let's say, times the number of pretzels, and I set that equal to $4.50, right, I can now solve for the number of pretzels that Parker would have had to have bought. Let me move this out of the way, move this up. 450 divided by 0.75, Parker would have to buy 6 pretzels. All right, simple enough. And of course, letter D has really almost nothing to do with systems of equations, right? It simply is using information that we found out in C in order to solve yet another math problem. Yay, another math problem. All right, so let me move this out of the way. Let's take a look at one last modeling problem. Now, geometric information, such as information about perimeter and area, often generate systems that can be solved, all right? So you always want to kind of be thinking about things like perimeter and area and whatnot when you look at systems. So let's take a look at exercise number 3. A rectangle has a perimeter of 204 feet. Its length is 6 feet longer than twice its width. Letter A, choosing appropriate variables, model the information given in this problem using a system of equations, where the 2 variables are length and width of the rectangle. All right, so go for it, right? Use appropriate variable names. I think you can probably figure out some good ones, right? And then model the information that they gave you with 2 equations and 2 variables. Pause the video now. Well, I think I'm just going to use the classic L and W for length and width. So I know the perimeter of a rectangle is 204 feet. What does that tell me? Well, that tells me that 2 times the width plus 2 times the length must be 204. All right, so that's just my perimeter. But I also know that the length is 6 feet longer than twice the width. So the length is twice the width plus an additional 6 feet. And there's my system of equations, right? 2 equations with 2 unknowns. Now, letter B, why would using substitution be easier than elimination to solve this system? Well, don't get me wrong. One could definitely use elimination, all right? But in order to use elimination, you would have to pull that 2w over to the other side of the equation. You could do that. You just subtract a 2w from both sides. But why would substitution maybe be our preferable method? Think about that for a moment and pause the video. All right, well, it's pretty easy, right? In the second equation, the L is isolated or solved for, right? So the L is all alone, which makes it so easy to substitute 2w plus 6 in for L in the first equation. So I'm going to say in the second equation, the L is solved for. By solved for, it just means that that variable is all by itself. All right? So now we have to go back a few lessons and we have to use substitution. Well, at least I'm going to use substitution. So letter C, find the width of the rectangle by solving the system. It doesn't even want the length, it just wants the width. Pause the video now and see if you can find the width of this rectangle. All right, let's do it. So I've got 2 times w plus, now I'm going to take this and substitute it in for that L. Be careful, that L has to be multiplied by 2. So I have 2w plus 2 times 2w plus 6. I'm going to now solve this by distributing the 2. All right, that's going to give me 2w plus 4w plus 12 is equal to 204. 2w and 4w can combine. 6w plus 12 is 204. I'm going to subtract a 12 from both sides. 6w is going to be equal to 192. I'm going to divide by 6 on both sides, and I think I'll bring out my smart view for that. 192 divided by 6 gives me a width of 32, and I should include proper units here. 32 feet. Always include proper units. 32 feet. Awesome, right? We wanted to get in one modeling problem there where it was more natural to solve it by substitution than it was by elimination. Now again, one could definitely solve basically any system using either one of the methods. It just is all about whether or not you have a situation like here, where one of the variables, is all alone, right? That L is all by itself on that side, so it's easy to take the 2w plus 6 and substitute it in for that variable. Or whether, like in the last two problems, once we've set up the system, all the variables are on the left side of the equation, right? And then it makes more sense to manipulate, add, eliminate, etc. All right, let's wrap this up. Where's my little forward button? There it is. Okay, so in today's lesson, right, we didn't learn any new algebra. We really didn't, right? We used the method of elimination and the method of substitution to solve systems. What we did do, though, and this tends to be pretty tricky for students, right? Understandably so, is we had to model problems using these systems of equations. It's all about properly defining your variables and then carefully translating the information that you are told in the problem into those two equations that you can then solve using one of the two methods. All right? You will get more practice solving systems of equations, but for now, we're going to be moving on from those and starting to look more at inequalities. I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.